Hello my friends, welcome back to the implementation of our network class, more specifically our convolutional neural network, for which so far we have built the convolutional layers and the batch normalization layers. And now, well, of course, what follows the convolutions are, of course, the full connections, right? Just like in a human brain, first the signal comes through the eyes, so we built the eyes first here with the convolutional layers, and then the signal goes from the eyes to the brain, which will be represented here by our full connections. Alright, so here we go. Let's start with the first full connection, which we're going to call, like last time, FC1. Self.fc1, which will be created as an instance of course, the linear class, which is a class that can build a full connection to build fully connected layers. And now the big question is, what is going to be the first argument here for the number of input features? Well, it's not that direct to get that number, because it's actually going to be the number of output features resulting from flattening all the previous convolutions. You know, that final flattening layer coming after the convolutions, well, that's this number that we're looking for here. How many neurons there are in this flattening layer. And well, there is a formula for that. The formula, if I remember correctly, is the input size minus the kernel size plus 2 times the padding, all that divided by the stride, and then plus 1. So you would need to apply this formula here first to get the output size of the first convolutional layer, then to apply this formula another time here to get the output size of the second convolutional layer, then another time here to get the output size of the third convolutional layer, and then finally another time here to get the output size of the fourth convolutional layer. And then by applying this formula 4 times, you would end up with the final output size of the flattening layer, which would be the input size of our full connection here. And so, well, we're just going to enter that formula without doing the whole computation. It's going to be 10 times 10 times 128. Okay, that's the output size resulting from all the convolutions we had before, which therefore is the input size of our first full connection here. All right, now, what is going to be the number of output features in this first full connection, meaning the number of artificial neurons in the first fully connected layer? Well, again, no rule of thumb, but a good architecture that works well here after some experimentation and hyperparameter tuning is actually 512 artificial neurons or output features in this first fully connected layer resulting from this first full connection. All right. Now, let's move on to the second full connection. Indeed, there's going to be another fully connected layer before the final output layer containing the action values. So let's do this. Let's build another full connection, self.fc2, which again will be created as an instance of the linear class because it's going to be another full connection leading to a new fully connected layer. Now, the number of input features is of course going to be the number of output features in the previous full connection. So therefore 512, and however now what is going to be the number of output features in this new fully connected layer resulting from this second full connection? Well, again, hard to guess, but after some experimentation and hyperparameter tuning, a good value here for the number of output features in this second fully connected layer is 256. Okay, alright, great, we're almost there. Let's copy this second full connection to create the third full connection. So I'm going to replace here FC2 by FC3, then replacing of course the 512 here by, well, it's going to be the number of output features in the previous fully connected layer resulting from the previous full connection, therefore 256. And now finally, what is going to be the final output size of our final output layer? Well, that's of course going to be the action size because it will return the action values. Alright, so we are done with our new full connections. Now we have basically the artificial neurons of our AI's brain that will be able to understand and learn the logic in the Pac-Man game, which of course will be understood with the deep Q-learning algorithm. Alright, so now what else do we have to do? Of course, we have to implement the forward method, to forward propagate the signal coming from this time the eyes and then through the artificial brain of the AI represented by the fully connected layers. So I can't wait to implement this method with you in the next tutorial. Try to practice it by yourself first, and once you're ready, let's mash this together in the next tutorial. And until then, enjoy AI. Hello my friends, and here we go. Now that we've implemented the convolutional layers and the fully connected layers of our AI's brain, well, let's define the forward method to forward propagate the signal from first the Pac-Man images to the eyes, and then from the eyes to the fully connected layers, and finally from the neurons to the body of the AI, let's say, that will be playing the actions. Alright, so let's do this. Let's start by defining this new forward method, which remember takes as input, well, first of course self for the object, and then state, which are the images. Alright, then colon, and here we go. So let's make some space, and let's implement the forward method. So, what is going to be the first step here? Well, it is to forward propagate the signal from the images to the first convolutional layer of the eyes. So let's do this. Well, how do we propagate this? Very simply, we're going to call our first convolution self-conv1, which of course is going to take as input the state, which is the image of the game Pac-Man. Okay, so that basically forward propagates the signal from the state to the first convolutional layer. And now let's continue this forward propagation. Let's now forward propagate the signal from this first convolutional layer to the first batch normalization layer. And how can we do this very efficiently? Well, very simply by calling our self.bn1 object, which is our first batch normalization operation, which is going to take as input, of course, well, this signal propagated from the state to the first convolutional layer. Okay, perfect. Then let's activate this thanks to the rectify linear unit activation function, also called the rectifier activation function, also called famously relu. And so how do we do this? Well, we're going to call our f module, the functional module, from which we're going to call the relu function, which will take as input all this signal, first propagated from the state to the first convolutional layer, and then from the first convolutional layer to the first batch normalization layer. Alright, great, so now we have this signal, and so let's create a variable for this signal, which we're going to call x, and which will be equal to all this. Okay? Great. And now the hard part is done. It's going to be super easy from now because we're just going to do some copy paste, because indeed the next phases of the forward propagation will be exactly the same by calling the convolution first on the signal x, and then calling the batch normalization, and then activating the signal with the relu function. So we're going to take all this, we're going to copy and paste it here. And now, according to you, what do we have to do in order to forward propagate the signal from our first batch normalization layer to the second batch normalization layer? Well, very simply, we're first going to replace here state by x, and then of course conv1 here by conv2, so that we can now forward propagate the signal coming from the first forward propagation to the second convolutional layer. And now we're going to forward propagate the signal from the second convolutional layer to the second batch normalization layer. And there we go, we are done. Now this signal x is forward propagated from the second convolutional layer and then to the second batch normalization layer. And so now let's copy this again to paste it right below, because indeed now we're going to forward propagate our signal x from the second batch normalization layer to the third convolutional layer thanks to our conv3 convolution operation. And then, of course, we forward propagate the signal from the third convolutional layer to the third batch normalization layer thanks to our third batch normalization operation. And that's done. Now the signal x is forward propagated to that third batch normalization layer. And finally, let's do that one last time. Let's copy this to paste it below and replace, of course, conv3 by conv4 in order to forward propagate the signal from the third batch normalization layer to the fourth convolutional layer, and then forward propagate the signal from the fourth convolutional layer to that fourth batch normalization layer thanks to that fourth batch normalization operation. Great, perfect, so we are done with those 4 sub-steps of this forward propagation. And now we just need to do a little reshape in order to reshape the tensor, in order to, flatten it. That flattening step coming after all the convolution operations. Well, that's exactly what we have to do right now. We have to reshape x in order to get that flattening layer in order to fit into the fully connected layers that come next. Okay? Alright, so let's do this. How are we going to flatten our tensor? Well, we take x first, from which we're going to call the view function, which will take as input first x dot size 0, and then for the second argument here we add -1. And what does that do? Well, that reshapes the tensor so that the first dimension corresponding to the batch remains the same and the other dimensions are flattened. Okay, so that basically flattens the tensor while keeping that first dimension of the batch. Okay, perfect. Then, now that we have the flattening layer, now that the tensor is flattened after all these convolutions and batch normalization operations, what do we have to do next? Of course, the forward propagation is not over. Now we need to forward propagate the signal from this flattening layer up to the final output layer through all the fully connected layers. And so how do we do this? Well, we know exactly how to do this. We did this in part 1 when implementing the deep Q-learning model. We're simply going to use our 3 full connections here. Alright, so let's do this. Let's take our signal X, then let's forward propagate this signal X from the final flattening layer to the first fully connected layer thanks to our first full connection self.fc1, which takes as input X, of course. And then let's activate this new signal thanks to the relu activation function. And this will result in a new signal X. Okay, and that's it. Now let's do some 2 more copy paste to smash this. So I'm copying this, I'm pasting the next one below. And of course, here we're going to replace FC1 by FC2 in order to forward propagate the signal from the previous fully connected layer to the second fully connected layer thanks to this second full connection. Alright, and finally, next and final step, we're going to return the signal in the final output layer containing the action values after forward propagating this signal from the second fully connected layer through the third full connection thanks to our self.fc3 full connection object, which takes as input X. And that's it, my friends. We are now done with the whole forward propagation, propagating the signal from the input images to the convolutional layers and the batch normalization layers, and then to the final output layer containing the action values through our 2 fully connected layers. So there we go. Now I guess you feel like masters of forward propagation. We did some great work here, and of course I want to say now congratulations, because we are now ready to move on to part 2, training the AI. Indeed, our AI now has some eyes and a brain, so we can train that brain into playing the game of Pac-Man. And we'll do all that in part 2, following those steps, which are almost the same steps as before, and we will use the codes we implemented before to do this efficiently. So there you go. I can't wait to see you in part 2 to train our AI, and until then, enjoy AI. Hello my friends, and welcome to this new tutorial, and mostly welcome to part 2, training the AI. Indeed, we now have an AI with a brain that besides has some eyes in order to be able to visualize some images, which will be the images of the game. And now, well, it's time to train that brain to play this game and get a good score at the end. So let's do this. We're gonna start with the first same step as last time, setting up the environment. And well, since it's almost the same, well, what we're gonna do is take our previous implementation, we're going to take the code that sets up this environment, and we're going to paste it back into a new code cell here to set up our new environment. And so what do we have to change here? Well, only one thing. That's of course the name of the environment. It is no longer Lunar Lander, but of course Pac-Man. And remember that we chose this variant, Miss Pac-Man Deterministic V0. Deterministic means that a small part of the actions of the other agents, meaning the monsters, will be deterministic. That will make the environment less complex. And V0 means that it's actually the initial version release. Alright, so we'll choose this. It is really the best for us to start, and mostly for us to train the deep convolutional Q-learning model, which is a powerful model but not the most powerful one, especially if we compare to H3C, which can solve here the most complex variants, including this one. So there we go, this one will be perfect, and besides we'll be able to train the model with the resources we have in our Google Colab notebook. Alright, so let's take this one. We're going to go back to our implementation, and we're going to replace Lunar Lander V2 by Miss Pac-Man Deterministic V0. And besides, just to decrease even more a little bit the complexity, we're going to enter here the full action space to be false. Alright, and that will basically ensure that the agent uses a simplified set of actions for Miss Pac-Man. And again, that will decrease a little bit the complexity of the environment, which will be better for us to train the model without having to wait too long or without having to have too much compute intensive resource. Alright, perfect. So now, well, we're done. We're done with this code cell. I told you it's almost the same as before. So let's run this cell, but first I remember that I forgot to run the previous cell, which builds a network class. So I'm gonna run it now and everything should be okay. There we go, perfect. We have the network class, and now let's run this cell to, by the way, remember, get the state shape, get the state size, and the number of actions. If you want, we can have a quick look at it. If we go back to the top here of the Pac-Man environment, well, we see that the action space is discrete 5, which makes sense, right? Pac-Man can turn left, turn right, go up, go down, and the fifth one might be do nothing, or, continue in the same direction. And this is the observation space, but I will tell you more about this when we make that preprocess frames function. All right, great. So let's go back to our implementation and, well, let's run this cell to see the state shape, the state size, and the number of actions. So what do we have? All right, so the state shape is images of dimensions 210 by 160 and by 3. So these corresponds to the RGB channels, the 3 channels of colored images. The state size is 210, but here that doesn't make that much sense. And besides, we won't use it for our implementation, so you can actually ignore this. And finally, the number of actions, well, 9. Okay, interesting. We just saw that the action space here is discrete 5, but maybe that's actually for the Pac-Man V5 environment, and Miss Pac-Man Deterministic actually contains more actions. Let me know in the comments what you think those actions are. Feel absolutely free to discuss, what you're learning through the tutorials, and if you want to make a comment, for example, you might know some things more than me, and well, I'm more than happy to discuss these things with you. All right, so let's go back to the implementation, and there we go. We are done setting up the environment. So now we're going to move on to the next step, initializing the hyperparameters, and of course we'll do that in the next tutorial. And until then, enjoy AI. Hello my friends, and welcome to this new step of the training implementation, initializing the hyperparameters. So it's going to be a super easy and quick tutorial because actually, as we said, we want to make this efficient, and therefore we're going to take the code from our previous implementation because you will see that it's actually going to be almost the same parameters. So in a new code cell, I'm going to paste that code section. And now indeed, well, the learning rate will stay the same. We'll take that same value of the learning rate. It actually appears to be a good one too for this Pac-Man environment and the deep convolutional Q-learning model. But after all, it's almost the same algorithm. It's just that now our AI has eyes. Then the mini batch size, well, we will actually change that. We will reduce it a little bit to 64. It appears to be a better hyperparameter value for the Pac-Man environment. Then for the discount factor, well, we will keep the same value of 0.99. It also appears to be a good one. And in general, we do want to reduce by very little the epsilon variable in the epsilon greedy strategy. Then for the replay buffer size, well, actually, we won't implement again the replay memory class as we did in module 1. However, we will still implement experience replay. Only we will do this in a much more simple way, not through the replay memory class. And therefore, since the replay buffer size was actually a hyperparameter of the replay memory class, well, we won't need it for our deep convolutional Q-learning implementation. And however, the interpolation parameter, well, we will simply remove it because we won't do any soft update. And why is that? That's because, very simply, the soft update doesn't really improve the training performance, neither the final results for this particular deep convolutional Q-learning model in this particular Pac-Man environment. I checked, so no need to implement any soft update in our future agent class. All right, so that's it. We're now done with initializing the hyperparameters. Now we're going to move on to the next step, preprocessing the frames. I can't wait to do that with you in the next tutorial, and until then, enjoy AI.